lower down this. Okay, we can start. So welcome everybody to the seminar of today. The speaker of the seminar is Alfredo Soldati, and today he will talk about modeling and computation of interfaces in turbulent multiphase flows. So as usual, I quickly introduce the speaker, and then I leave him the stage. So Alfredo Soldati is a professor of mechanical engineering at TU. His research focuses on physics and engineering of multiphase flows. Dr. Soldati received the 2007 Asmer Robert Knapp Award, in 2015 the Asmer Lewis Moody Award, and in 2020 the Asmer Freeman Scholar Award. In 2013, he was elected Fellow of the American Physical Society, and in 2020 was elected Fellow of Euromech. He also received the International Prize and gold medal Panetti Ferrari in 2018 from Accademia delle Scienze Torino, Italia. He is currently director of the International Center of Mechanical Sciences, CISM, and the co-editor-in-chief of the International Journal of Multiphase Flow. He maintains part-time position at the University of Udine, Italy. Is it with great pleasure that I introduce Alfredo Soldati for the talk of today. Professor Soldati, I leave you the stage. I stop sharing my screen.
Well, first of all, while I'm trying to share the screen, I need to thank you very much for not only having invited me, which is a great pleasure, but also for taking care of organizing this series of seminar, which I believe it was crucial and important as a platform for ideas exchange during this time in which we could not exchange ideas in any different way. So thanks a lot for your effort and for your dedication to the community of fluid mechanics. Second, I would have much liked to be in Lille to give a seminar in presence that we can do perhaps at later stages, not now. But I'm anyways very much pleased to share with you some of the results we have obtained in the years with my group, specifically regarding the breakage, coalescence, and the resulting drop size distribution using the phase field method and the direct numerical simulation of turbulent. The picture you see is actually not a photograph, it is the result of a simulation. So there is not much rendering, it is just the result of a simulation, which in my view seems very real. And from this picture, you can definitely see small drops, large drops, deformed drops. And this is the aim of our research, to try to simulate all the possible development and the modification of drops in a turbulent flow field. What is the problem in this case? The problem in this case, you want to do the simulation, is the problem of scale. The problem is a multi-scale problem. You have the turbulent flow, so the large scale size of the system. Then you have the flow in between the drop size scale. So you have the scale of the drops, which can be different from the scale of the main turbulent flow. And then eventually, if you look even closer to what happens, you have the molecular scale. Now, this problem is definitely impossible to be solved with all the scales nicely and fully resolved. So we need somehow to place ourselves in this nice plot, which puts the characteristic drop size as with the resolved scales of the method. So here is the scale of the drop size we want to simulate, and here is the resolved scale of the method. Of course, here we can consider several approaches. We will focus just in this talk on the interface result simulation. So we want to see what happens if you are able to resolve the interface of the simulations. In our simulations, all the turbulent scales are resolved, and the droplet size is comparable. Definitely, we cannot impose it to the turbulence scales. So it's the red square which will be the focus of this talk. Now, this is the outline of the talk. I will start with an historical perspective and with some computational issues. First, the history. Now, the history is as follows. Many years ago, Benjamin Franklin was sailing back from US to UK, And he was actually seasick, and he was just moving with the waves. And he was surprised to see the other ship, one other ship that was sailing very smoothly through the waves. So he asked his captain, and he asked him why this ship is sailing so smoothly. And the captain told him maybe it is some oil of the kitchen that was thrown outboard, and the oil has remained attached to the keel, so that the waves are actually calmed. So this was a first scientific not the first, but it was a scientific observation of what can be the effect of a surfactant on the interfaces. Later, with jumping through the years, Lord Rayleigh started to investigate on this problem, and he came to a measure of 1.63 10 to the minus 9 meters as the thickness of an interface. And then Agnes Pockels, she was a woman, a German woman born in Venice. And at those times, it was impossible for women to study at university. So with the help of the books of her brother, who was studying physics, and with the help of the kitchen as a laboratory, and you know that in the kitchen, you have plates to wash, dishes to wash, and then you have water, and then you have soap. So you have interfaces and surfactant. She was actually able to invent a scale to measure the interface to a precision which was much more accurate than that of Lord Rayleigh. Than that of Lord Rayleigh. She was actually eventually able to publish her paper on Nature, and eventually she was given a doctorate. Now, if we have two drops that interact, I will replay this video because it went very quick. You see that these two drops eventually coalesce and become one drop. You see that the coalescence event is a dramatic event which will happen immediately over a very short scale of length and in a very short scale of time. This event is one of the problems which we face in our simulations. But we don't want to simulate two drops that coalesce in a quiescent flow, but we want to be able to simulate these works have been done, and there are many works. So drops that can coalesce and break in a number of control situations. We want to do the coalescence and breakup of droplets in a fully turbulent flow field, in which you have the effect of turbulence, in which you have the effect of turbulence on the modification on the interface. So you have an interface dynamics, and then perhaps you have the surfactant dynamics, which moves non-homogeneously on the surface of the drop. So we want to be able to tackle a real turbulent multiphase problem with the instruments that we have. The problem is that the instruments that we have will have to be able to predict the following distribution. Now, what is our interest is to determine, after all this coalescence and breakage event of these drops, a final drop size distribution. And the drop size distribution is determined by simple factors. You have a drop with an interface. The interface can be considered as an elastic membrane which can oppose some resistance to a shearing motion. Now, the interface can oppose some resistance to the shearing motion until it breaks. So this is a breakage event. Then if two drops are very close, as you've seen before, then they can coalesce. Now, this scale, the scale at which the drop cannot break due to the shearing event is called Hinze critical radius. It is the radius below which drops usually don't break. And this can be measured via some estimation of the level of turbulence and of the Weber number, which is a measure of the surface tension. Now, we want to be able also to have a scaling of what is the distribution of the radius for small drops. And this can be done through some theoretical estimation. Please look at the paper by Garrett and Farmer, and also for the drops which are a bit larger. Now, drops which are larger are continuously forming, and then they eventually break because they are above the Hinze scale. And you see, in fact, that the slope is a bit steeper than the small drop scaling. Now, This scaling is what we would like to be able to predict with the computational method, not just as a scaling, but as the result of a number of coalescence, detailed coalescence and breakage event simulation. Now, the problem, as I said, is the scale separation. If you want to consider for simplicity an homogeneous turbulent flow, an homogeneous turbulent flow, let's suppose a 1 meter side box, you will have the smallest scale, which is 10 to the minus 9 meters. So you have to be able to simulate, turbulence. The smallest scale is 10 to the minus 3. So you have 3 orders of magnitude scale separation. So if you want to make a direct numerical simulation, you can use 10 to the 9 points, feasible. If you want to be able to tackle the interface simulation, you have 9 orders of magnitude, so 10 to the 27 grid points. Now, each big supercomputer can now tackle only up to 3 or 4 orders of magnitude. And so the choice is where you want to put this resolution of the computer. You can consider the interface, or you can consider the large vortices. Now, if you want to simulate a problem which has some hope to reproduce the reality, you have to put these 3 or 4 orders of magnitude, which the supercomputers will give you in resolution, to the largest scale. So, of course, we cannot definitely go to the smallest scale. So what can we do? We have to consider some artifact related to the interface. But before doing that, I will tell you what is the multiphase flow simulation with interface tracking based on. It's based on 2 ingredients. One is the flow field solution, as you always need, and the other is the interface tracking. For both of these ingredients, you can use a sharp approach or a continuous approach. And let's start with the flow field solution. The red arrow tells you what is the approach we are using. In the sharp approach, we can find the family of the ghost fluid method, and we can find the method of the force coupling. The Tryggvason and his co-workers have made wonderful work with this force coupling method, which is actually in the continuous approach, and the phase field model, which is the one we will do. For the interface tracking, we can also use the sharp approach and continuous approach. The Tryggvason and co-workers are using the front capturing. Scardovelli and Zaleski, for instance, in Annual Review of Fluid Mechanics, and there are many people, a lot of works in this field are using the volume of fluid. Among the continuous approach method, you have to use a level set. You can find the level set or the phase field model on the Canillier model. So we are using the following equation to simulate the position of the interface. What does continuous approach mean? Is exactly the following. If you have a sharp interface, until here you have a drop, immediately next to it you don't have a drop. So it's yes or no. But if you have a continuous approach to solve the interface, you can see that the interface is actually diffusing. It means that the color function, which is phi in our case, or the phase indicator, can go from 0 to 2. And conventionally, we can put the interface at some value, which is exactly in the middle. So the interface, sorry, phi should be here. It should go from 0 to 1. This is wrong. So the interface is conventionally put at 0. And this is the place where we place our own interface. Of course, you can find some traces of the color function of one phase into the other, fading into the other, and vice versa for this. The point of what we do is actually that in order to reduce the computational effort required, we must fictitiously enlarge the size of the interface, and we have to put it fading on the right side and on the left side of the conventional interface. But these are some advantages. If you look up here, and if you consider the sharp interface approach, normally you prescribe the interfaces and you assign properties to it. Properties normally are models. With the phase field approach, you could prescribe the properties of the 2 fluids, You define the interface to be in a conventional place. So the properties of the two fluids which are interacting through the interface are prescribed by physicochemical laws. Now, this is the frame in which I am telling you the next three stories. And I have separated the seminar into three short stories. The first will be of droplets in turbulence and the influence of viscosity and density contrast. Now, I'm starting with this famous picture by Gretar Tryggvason, in which he was demonstrating the role of surface tension in deforming the bubbles. How can this be an effective mechanism to strongly modify turbulence? And I will go to what we are doing. And what we are doing is a very simple experiment. So we consider one experiment in which you have two different fluids with matched density, so same density, with matched viscosity, so it is essentially the same fluid, but we assign a surface tension, which is constant. And the surface tension has a very important property, because whenever you modify the shape of the interface, the surface tension will react with a force which is perpendicular to the interface itself. Now, this changes the Navier-Stokes equation, because you have the continuity equation, which is the same as before. You have the Navier-Stokes equation in which a new term appears, which is a stress, which is caused. It's called capillary stress, and it is caused by the effect of surface tension. So it's a back reaction on the Navier-Stokes equation. And then we have an advection diffusion equation with which we describe the behavior of phi. And I remind you, phi is the phase indicator, -1, one fluid, +1, the other fluid. Now, some experiment. We did some simulations changing the Weber number. The only thing we can change in this setup is the surface tension. So eventually we are changing the Weber number. Remember, the Weber number is the inverse. It's proportional to the inverse of surface tension. So small Weber numbers, 0 Weber numbers is a rigid fluid spheres. Infinite Weber number, you don't have surface tension. We will focus on an intermediate value. I mentioned here the value of the shear Reynolds. It is just a measure of the turbulence intensity, but what is important here is the Kahn number, which is a numerical parameter, which in fact tells us how much the interface is diffused on one side and on the other side of the drop. So it is related to the resolution with which we describe the interface position. As you see, the grid is very large. The resolution is over-resolved comparing with a single phase direct numerical simulation. And let's see some of the results. We have a flow field. Initially, the flow field is a pure single phase fluid. And then we start putting some drops. And the drops, we can put the drops like in a real experiment or in any other method. We can start from single drops, or we can start from a sheet of liquid. And then we will have a drop that will form due to the surface tension, and that will break and interact and separate. Now, the two phenomena which we can observe in this case are coalescence and breakup. Coalescence, as you've seen before, it's very slow until the end, where it becomes very fast. The breakup is always fast. So the problem which we and all the people who are doing this type of problems have to tackle numerically is that coalescence is hard to predict numerically. So you can find mistakes in the coalescence rate. Breakup, you can find less mistakes. Let's start with a conventional initial droplet number, which is N0. And we see that starting from this initial conventional droplet number, the number of drops decrease. And it decreases in different ways according with the value of the Weber number. So if we have the gray symbols, the surface tension is so strong that breakage is impossible. So the Hintze scale is very large. Breakage is impossible, and only coalescence is possible. And you see that the number of drops dramatically reduces. But if you decrease the Weber number, then at some point you can find with the orange line and with the green line that you reach almost a plateau. And this plateau is due to, it occurs when the coalescence rate and breakup rate are equal. You see that even the shape of the drops are much different if you have a very low surface tension like the green thing, or a very high surface tension like the purple picture. Now, we have seen what happens just adding the surface tension. Now we want to make a little more difficult experiment. We want to see what happens if we change the viscosity. So if we change the importance of the dissipation inside and outside the drop. And the drop viscosity, the continuous flow phase viscosity, is called lambda. Now we will change lambda. If we change lambda, we have to face some other problems from a numerical viewpoint, because we have to split the viscous term and we have to put the viscosity inside the first derivative of the Laplacian, and we have to solve the problem in this way. How do we model the difference in viscosity? Just as a linear function, a proportional function to the phase concentration. So viscosity will change exactly as the phase proportion. So we have to put this term. Still, we have again the capillary force term that, I remind you, is acting perpendicular to the interface in all positions. Now let's see what happens. This is a table of all the simulations that we did, and we have lambda, which goes from drops with very small viscosity or drops which have very high viscosity. So this can be water in oil, and this can be oil in water. And we change also the Weber number. You see that if we go with a Weber number, which is very small, so strong interface, strong surface tension, then even if we change the viscosity, nothing really happens. But if we start to reduce the surface tension, we will see that something happens. And in particular, if we go to this, which is easier to explain, we have a very small surface tension. And if we increase lambda, so we have drops which are much more rigid, then what happens is that the rigidity of the drops forbid breakup and enables only coalescence. So a rigid drop, if you have a drop which has a very high viscosity value, then it will behave like a drop with a very high surface tension. And this is due, of course, to the large dissipation, the turbulence motion, and all the motions that are transmitted to through the interface to the inside of the drop. They are dampened much more efficiently by the strong viscosity. This is the phase. What are we looking? This is the shape and the appearance of the drop. You see that if we change just the viscosity of the drop with the same surface tension, we see that drops behave in a much more rigid way. We can also change the density, and in this case, we changed the density. Now, you can tell me that the density changes also the viscosity. So we made an artificial experiment. We just changed the density, but we kept the viscosity the same in order to examine the role of these two variables separately. And we see that if we change density of the drop, only the density, not the viscosity, it doesn't really change much. The picture doesn't really change much. You see all the red lines almost overlap, all the green line almost overlap. So not much of a change if we just change the viscosity. In the next seminar, I will tell you what happens if we change both density and viscosity at the same time. And now I change the subject just to make a little more confusion and try to distract you. And then I will speak again about drops. This is a short story on oil transport, which is a problem that is fascinating me. And this problem is the following. Now, it is known since many, many years that if you have a highly viscous fluid like oil, and if you put water in a certain way, the water will actually go outside. Water is much lower viscosity than the oil. Water will go outside in the pipe, and the oil will go inside the pipe. So now what happens? Since the viscosity of the water is much lower, then if you pump the fluid, the reaction shear stresses on the pipe will be proportional to the viscosity of the fluid, which is water. So you are pumping oil and water, but the pump will believe that you're just pumping water. And this is almost a kind of a gift of nature. I'm using the words of Dan Joseph. And the lubricated flows are stable, so they don't really oscillate much, they don't break. And actually, you can really save a lot of energy in pumping fluid. Now, these things are actually used in industry. And we wanted to see with the following simulation I'm presenting, if there is any effect of surface tension, or all the effect is due to the change, the viscosity contrast of the two fluids. So what did we do? There is a pipe. We cut the pipe on one side and we open the pipe so that we can simulate a channel. And here you see the same channel, which is just a topological change of the open pipe. The gray thing is water, so smaller viscosity. Black thing is oil. And you see that there are waves forming at the interface. And these waves, in these waves appear these nice red blobs. What are these nice red blobs? These red blobs, it is just the extent, so the intensity of the capillary forces. So the red things are just the surface tension forces. So we are showing you that when the interface is flat, no surface tension forces. When the interface starts to deform, the capillary forces immediately wants to put back the interface to its flat position. These are the equations that we are solving as before. And what did we find? First of all, we did some simulations. Now, all the simulations that I'm presenting you are simulations that are done exactly like in an industry. So we are maintaining the power, so the product of the pressure drop by the flow rate. So the power input is constant. So if we change the flow rate, also the pressure drop will change. And we are giving one surface tension characteristic of an oil-water interface, and we are also changing the interface, going from smaller to large. Now look at the mean flow profiles. The mean flow profiles, you see that there is a strong change in the mean flow profile. So there is a strong and very important drag reduction in all the cases that we examined. And the cases that we examine go from a factor of 4 smaller viscosity of the liquid layer to 4 times larger viscosity in the liquid layer. You see, however, that even if there is all the times an increase of the average velocity profile, the slope of the average velocity profile, which goes towards the wall, changes. A synthetic summary of the problem is here. Here on top, you have the flow rates, and at the bottom, you have the pressure drops. And you see that low viscosity layer, you have always less pressure drop, unless you go to a very high viscosity layer. So only if the viscosity of the layer is 4 times higher, you have a pressure drop increase. And all this pressure drop decrease are essentially due to the surface tension. Let's see what happens. Now, here you have a single phase flow, and here you have the 2-phase flow. Here you have the layer above the white line, which are the waves separating the two fluid. You have the same viscosity fluid, and here you have a very lower viscosity layer. Now, I cannot stop the image, or maybe I can. Look at here. You see that the layer here is almost laminar, very quiet. Here, it's very turbulent, obviously, because if I locally reduce the viscosity, it is like locally I am increasing the Reynolds number. So even if the layer is very small, if I reduce the viscosity, then I am actually increasing locally the Reynolds number. One important point is that here you see lots of red, which indicates high velocity, much larger than the velocity I find in the single phase. Now, this is what happens if you look in the front rather than on the side of this flow, and you see, of course, what I said before. So if I have a low viscosity, I have, this is just the turbulent kinetic energy, but it tells you just how much turbulence activity is in the liquid layer. A lot of turbulent activity because there is low viscosity, not much turbulent activity, very little turbulent activity, very, very laminar. But the point is that I am able to reduce drag regardless of the fact that the lubricating layer is laminar or turbulent. And this is a very important result because it's telling us that most of the drag reduction is due to the surface tension effect, at least for this range of values of the viscosity. Now, what is the role of the capillary stresses? Now here I'm showing you the mean velocity. You have seen that the mean velocity, it's not, it has a kink in the profile. And this change of steepness, this change of derivative is due to the capillary stress, which can act only at the interface. And the capillary stress complement very nicely the total stress, but this means that the local viscous stress must have a dip in correspondence with the capillary stress. Here, there is a more accurate representation of what I just told you. And you see that always the capillary stresses, which are the green ones, go to complement the turbulent stresses and the viscous stresses. But in this area, so in the area around of the interface, the behavior of the stresses is rather complicated because the capillary stresses enter into the balance. Now, I will just skip this slide, and I will go to a short story on drop coalescence. And I will tell you about the influence of surfactant, which is, in my view, a very intriguing problem. Now, I told you what is the phase field about. The phase field is about putting a phase indicator, which here is in red, which goes from -1 to +1, from outside to inside the drop. And it can go across the interface with a certain slope. Now, if we want to put the surfactant, we need to use another phase indicator, which we'll call psi. And this surfactant, however, have interesting properties because the surfactant can do several things. First of all, it can be dissolved in the ambient flow. So there is a certain, although very small, value of the surfactant that can be dissolved into the outer flow or the inner flow. Then the surfactant likes to stay at the interface. So we gave this assigned the surfactant a property that makes it like to attach to the interface. So here you see a local maximum of the surfactant. Naturally, once the drop breaks, the surfactant can actually be freed in the main fluid, and then it can go again on the interface or on the interface of another drop. So in our problem, we are actually simulating the total amount of the surfactant, which can go everywhere according to where it is needed. Here there is a representation a little more accurate of what is the distribution of the surfactant. And it is important to assign psi a value, which is the bulk value. So the bulk value is the amount of surfactant that we throw into the entire flow. So remember psi bulk. Now, equations now are becoming even more complicated. And so we need to have, an effect of the surfactant on the drop, on the surface tension, because from what you know that always the surfactant reduces the surface tension. And this is, of course, very nicely understood. I will mention something here, that the surfactant is able to produce Marangoni stresses which can act tangentially to the interface. I will discuss this a bit better later. And eventually, even the advection diffusion equations for phase and surfactant become a little more complicated because, of course, the surfactant as the advection diffusion equation of the surfactant is influenced naturally by the distribution of the interface, because we want the surfactant to go towards the interface. The Navier-Stokes equation change, and they change in a very important way. Apparently they don't change really much, because there is the capillary stress, which is multiplied by F sigma. F sigma is a function of the interface of the surfactant concentration. F sigma is called intensity of the surfactant. So if you have a soap which is much more intense, F sigma is increasing. So it is the amount by which the surfactant can reduce the surface tension. So there are two parameters of the surfactant. One is the intensity of the surfactant, and the other is the amount of surfactant that is thrown into the flow. First of all, I will show you an experiment. And this experiment has been published on Journal of Fluid Mechanics more than 20 years ago. It's a beautiful experiment made by our colleagues in Napoli, Guido and Simeone. And the experiment is the following. You have two plates that move in a wet flow. And then you put two drops. So these are two drops in a liquid. And these drops actually are moved one against the other. You see from the sequence A, B, C, D, E, F, that these two drop in a certain condition of surface tension value, a surfactant value. They initially start sliding on top of each other. Then they are on top, they form an 8, and then this 8 is actually stretched, and eventually the two drops coalesce from the tail side. If you add surfactant, what happens? You have exactly the same parameters of the surface tension, but you add the surfactant. If you add surfactant, what happens? In principle, the surface tension is smaller. So the drop can deform better, and the drop can actually slide on top one of the other. So this is essentially what happens. I will detail a little bit more in a better way what happens in between the two drops once they tend to approach or slide on top to the other. So this is no surfactant and surfactant. We have done exactly the same simulation in a very controlled situation to prove our method of including the surfactant, and we examined a number of cases. When I say we, I mean Alessio and Giovanni, who did, I will thank them in the end, who did most of this part of the work. And the red dot indicates when there is coalescence. The white dot indicates when there is no coalescence. And this plot is made changing beta S, which is the intensity of the surfactant, with psi B, which is the bulk concentration of the surfactant. So we can change the concentration of the surfactant and the intensity. And we see, of course, that the situation is very different from this point to this point. No surfactant, blue dot. Here we examine these 2 points, the points in which we have coalescence and the point in which we don't have coalescence. And of course, the deformability of the drop changes with the capillary number. Now, we will examine these 2 extreme cases, and I will show you pictures of this and movies. And look at this. This is exactly the same experiment that Simeone and Guido did. And here you see the blue thing is not fluorescence, is actually the amount of surfactant. So you see that there is surfactant, but in this case, it's not enough to prevent coalescence. And in the other case, it is enough to prevent coalescence. What happens here? Mechanism of coalescence. When 2 drops are approaching one to the other, then the 2 drops, in order to coalesce, in order to merge their interface, must remove the fluid in between. So there must be a gap draining. So the gap must be drained so that the 2 drops can coalesce. Here you see the color code is such that the black is lot of surfactant and white, very little surfactant. What happens when you have get draining with some surfactant? It is that there is a shear stress. This is a typical lubricating flow. You have a shear stress which is forming, and the shear stress is actually acting on the surfactant, and just by shearing effect is draining the surfactant from here to here. So here you have the surfactant which is non-homogeneously distributed on the interface. Now, what I told you before is that the surfactant can actually do the following. Since there is a surface tension gradient, then the surfactant wants to go back to, because it wants to stay homogeneously distributed. So there is a surface tension gradient, and the surfactant is actually trying to get back to the position. And in trying to get back to the position, it is generating some shear stresses, which are actually called Marangoni flow, which will prevent the gap draining effect. This is the mechanism that prevents coalescence when you have surfactant, and it is very interesting. Now, look at here. Here is when there is no surfactant, and here is when I throw some surfactant into the fluid, and yellow is a lot of surfactant, red is little surfactant. You can see that all the times when the drops are into the fluid, surfactant is not homogeneously distributed. And this depends on the shearing action of the turbulent flow field, which changes the distribution of the surfactant on the drop. Now, the problem of the surfactant and surface tension and turbulence is very complicated, because initially there is, suppose you have an initial uniform distribution of surfactant, then you apply shear stresses due to turbulence, then you will have a modified concentration of distribution of surfactant on the interface. And again, you will have shear stresses produced by surfactant, which are called Marangoni stresses, which will modify the stress distribution of the drop. So the problem is very intricate. Here, you will see what happens in our flows is coalescence and breakup. And I will ask a question later to the students. What happens to the drop I am indicating here? You will have to respond to me later. Now, let's see in general what happens. This is Weber number 1.5, and this is Weber number 3. I remind you, Weber number 3, low surface tension. Weber number 1.5, higher surface tension. This is the number of drops. If I increase the intensity of the surfactant, so red is a strong surfactant, I am reducing surface tension. And if I am reducing globally surface tension, I'm actually having more drops. That is intuitive. So, because there is more breakup. These are the two pictures of the two qualitative pictures of the phenomenon. The same occurs, the same happens for Weber number equal to 3, so lower surface tension. So you will see that you have a larger number of drops, and possibly because there is less coalescence. But the point is that, are we sure that there is only less coalescence? For sure, there are more drops, and for sure, there is less coalescence. But if you look at the accurate determination of the breakup rate and of the coalescence rate, you see that not only the coalescence rate is changed by the presence of surfactant, but also the breakup rate is changed by the effect of surfactant. So both are increasing. And since the number of drop is essentially made by the breakup rate minus the coalescence rate, so coalescence is the death of the drop, and breakup is the birth of the drop. So you have the number of drops that are born minus the number of drops that die, and eventually you have the change in number concentration of drops. And you see that surfactant actually modifies both rates, but a little more the coalescence rate. In addition, you have also to consider that if the surfactant increases the breakage rate, you have around in your flow more drops that have more probability to coalesce, because coalescence is not only depending on the property on the interface, but it depends both on the property of the interface and on the probability that one drop finds another drop which is very close. Now, let's see the final plot, which is the holy grail of all the people who work in sprays and atomization and drop size distribution. This is the Hind's diameter. And you see that the Hind's diameter, so here there is the equivalent diameter of a drop, and here is the probability of finding a drop with this size or with this size. The Hind's diameter changes with color, and because we are changing the surface tension. So we are changing the resistance of the drop to breakage. Red indicates very flexible drops, very small surface tension. Here you have, for the small drops, you have a more or less constant plateau. And then for the drops which are larger than the Hind's scale, we have, I would say, not an indication that this scaling is wrong. So we cannot prove that our simulation really follow this scaling, because you see that our plots, our dots are not really on a straight line, but we can definitely not disprove this scaling. You see that the white dots are actually essentially the same, red-white dots are essentially the same as the red dots, but one of the reviewers of our paper asked us to run a simulation at twice the resolution. It took 2 months, but then we produced evidence that the major scaling does not really change. The only thing that you can notice is that, of course, if you have a smaller, finer resolution, you can afford a better description of the interface and therefore a larger number of smaller drops. Now, I'm thanking you for the attention, and I really have to thank all the people that have been working on this problem. Most of the work that I presented has been done by Alessio and Giovanni. And the question with which I'm ending the presentation is that people say that nature should be continuous or should be discontinuous. If you use phase field, you are forced to think that nature cannot be yes or no. It can be yes, yes, no, yes, no, yes, no, no. So thanks again, and I'm available for questions you might have.
So thank you for this very interesting presentation and for the several aspects you considered in presenting. So I would say let's just open the stage for questions. If there is someone who has a question, just feel free to unmute your mic and ask your question, please. You can also write in the chat if you have any question you would like me to read. Then
no questions.
Yeah, just to start. Maybe they are muted.
Maybe you should unmute them.
Yeah, that's. I think they.
I may have a question.
Okay, go ahead. Yeah, that's right.
Good evening, Professor, and thanks for the very nice talk. I'm Marco Crialesi from KTH. I actually have a question on the minus 10^3 distribution that you showed. It's been a few works right now published in literature where they found this type of distribution in coalescence, in presence of coalescence. But if I remember correctly, the original distribution was actually discovered, or let's say derived, for lack of coalescence in some kind of dispersed flow from Garrett. It's very interesting to me how this can actually be captured when coalescence is occurring. And could you comment on that, please?
Well, Garrett made this experiment, made this theory, in fact, considering breaking waves. That was his major topic of the problem. I'm not exactly sure of what happens when you have wave breaking, and the distribution was made for bubbles, not for drops. Having said that, there is no difference between a bubble or a drop if you just consider the surface tension. And having said that, also there might be coalescence in the drops or in the bubbles. I'm not really sure what is the implications of the theory of Garrett. I'm pretty sure that the theory of Garrett was demonstrated not demonstrated, but benchmarked later by Dean and Stokes with detailed experiments on wave breaking. And eventually, there is another scaling law which has been derived and not based on forces. This is based on forces scaling, but it was based on energy scaling, and it was derived by Deike, by the group that is using the VOF approach, and they came to the conclusion that the real scaling is -3, not -10^3. Now, the difference is low, but between -3 and -10^3, if you don't have really extremely careful experiments or simulation, it's really a matter of very slightly slope. I am not sure I can comment on exactly what you said, but I hope that this is enough.
Yes, thanks. It's actually almost answering my question.
Okay.
Thank you.
Someone who has a question.
Think Raja.
Hello, Professor. This is a very interesting talk, and I'm Raja from India. I'm a fluid mechanics student, and it's quite interesting talk on multiphase flows. I'm just curious about your second part of the talk on two-phase flows near these interfaces, and by decreasing viscosity, very near the wall layers become turbulent and try to pull out, or perhaps creating a lot of turbulent zones. So will that interface also try to have any effect on that, like expulsion events, and the second, I mean, the other phase is trying to pull into these turbulent boundary layers, mixes up,
yes,
and again
definitely.
Expulsion happens.
Definitely, yes.
Okay.
But I can elaborate if you finish your question. I can elaborate. Otherwise, I let you finish your question.
Oh yeah. So I'm just wondering about these distribution of these phases in those turbulent boundary layers. How are they going to really affect the wavy motion compared to typical annular flows, what we try to see like wavy dynamics?
It is the same, but I mean, what you're saying, if I understood correctly, is let's suppose I have a wave which is going up and down, and here I have the wall. In the wall, I have a turbulent boundary layer. The turbulent boundary layer is characterized by a structure. If I have waves going up or down, then I may have an expansion of the boundary layer or a compression of the boundary layer. If I have an expansion, maybe structures are more free to interact. If you have a compression, maybe structure will die. There is a very famous paper by Reynolds and Hussein in the 70s, which tells you exactly what happens in this case. But definitely you're right. Once the boundary layer is compressing, then turbulence is almost killed in that area. Once the boundary layer is expanding, then turbulence is actually able to, say, interact better. So there is a strong influence of the wave structure on the boundary layer. There is also an influence of the boundary layer on the wave structure, because of course, initially the waves are produced by some momentum coupling, which is coming from the boundary layer. So the coupling between the interface dynamic and the boundary layer dynamic is definitely strong. I didn't elaborate on this during my presentation because it was not possible, but of course there is a very strong coupling.
I see. Thank you so much, sir. So nice.
Sure.
Can I ask a question?
Yeah, please go ahead. I think you can try to speak a little bit louder if possible.
Sure. Can you hear me?
Ciao Roberto. Ciao Roberto.
Yes, Alfredo. It's a beautiful presentation. I have to congratulate because it was very clear Very nice. I have two questions. The first is about the first problem, the one regarding the influence of viscosity. Just curiosity. If it is the initial in the initial condition, you just put that you have say drops, spherical drops of course of different viscosities, and now you can somehow simulate the flow. You should be able to find how an effective viscosity depends on the viscosity, on the ratio, on the lambda parameter that you have introduced, the viscosity ratio between drops and continuous phase. We know, for example, in the case of the blood, in case of having when you have a volume fraction of about 0.4, 0.45, you have that the effective viscosity of the blood, where the particles are clearly elastic and can move from one side to the other. In that case, the effective viscosity is about 6 times the viscosity of water. But on the other hand, if you have a rigid body suspension with volume fraction of 0.4, 0.45, now I don't know, but the effective viscosity is about 100 times larger. So I wonder if you can somehow simulate that case and find some explanation, some clearer explanation of what I just mentioned.
Well,
that's the first question.
Okay. Oh, if you want, I can. Let me answer first the first question first, so I will not forget. I know that in problems where you have a suspension of solids, if you have much solids, then you can find an effective viscosity of the homogeneous mixture, just doing some interpolation between the two viscosity values. Now, in our cases, of course, we have drops which have 100 times viscosity, 100 times larger than the fluid, but the percentage, the amount of the concentration of drops in our case is rather small. So it's rather dilute flow. It's few percent. It's not really much. Now, we never try to simulate to investigate on the effective viscosity, but one thing we did is to measure the pressure drop. If we had a change in the effective viscosity of the mixture, then we should measure a change in the pressure drop of all this mixture flowing into the channel, and we found minor differences. So in our case, perhaps the concentration, the number concentration of drops, so the amount of drops is too small to strongly influence the average coalescence, the average viscosity of the entire mixture. But of course, your point is worth investigating. Actually, you gave me a very good idea for next simulations.
That was my idea.
Yeah.
The second question is regarding the third point. I mean, in your phase field model, you have a parameter phi going from -1 to 1, and in between there is a certain curve connecting the two values, inside and outside drops. Presumably, you use the hyperbolic tangent.
Yes.
Or yeah, something like that. The question is how thick it is. So my question is and now on one hand, you know, we could start discussing about the fact that actually this width should be proportional to the surface tension, but that is true only if phi, the parameter phi, is a real physical quantity. While in your model it is and it is not, I mean, not completely. But my question is very simple: how sensitive is the result eventually? How much does it depend on the thickness of this arc tangent, tangential hyperbolic arc tangent going from -1 to 1?
Well, it does depend. Everything depends on that. It is an important parameter of the simulation. This is the Kahn number, essentially. The Kahn number measures the thickness of the interface. So the space it takes for phi to go from 1 to -1. That is measured by the dimensionless Kahn number. Now, in the last simulation, in the last plot I've shown you, we doubled the resolution. If we double the resolution, we are also able to reduce the Kahn number in half. So we have an effect on the thickness of the interface. Let's say this with these bad words, because the interface has no thickness, more or less, in our case. But the results depend on the number, but mostly on the size of the smallest drop which can simulate. So we can simulate smaller drops when we decrease the number. So this is there is an influence, but yes, I mean, we always, in addition, our grid is not uniformly distributed, is not uniform. So we have near the walls a very fine grid, and in the center of the channel, very large grid points. So we take care, we ensure that everywhere we have between 3 and 5 points of the grid to simulate the interface. Of course, doubling the grid, we have these 3 or 5, it depends on the points rather than on the thickness. So if we have a double grid, if you double the grid, then these points occupy a smaller region of space. But definitely there is an effect. Now, if I told you, I would like to ask you a question, and if there is no answer, I'm asking you, not you, Roberto, but everybody a question. And can I? In fact, I did ask.
Yeah.
And the question was, in this problem, in this simulation, and look at here, this small drop, it will disappear. Now, I asked Giovanni and Alessio, where is this drop going? And they came with an answer which is not mine. So that is the answer of the person, the scientist that has done the simulation and has complete faith in the simulation. And my question or my answer is actually the answer of somebody who does not trust the simulation. So I asked Giovanni and Alessio, and they told me, well, this drop is actually disappearing because it goes beyond the border of the boxes. It goes beyond the face of the box. You see that it tends to go in this direction, and it goes perhaps beyond the box. Or the other explanation is that this drop is actually becoming smaller than the grid size, and then it disappears. So this, I am not able to have a very small canal, and this is something we don't like to have.
So basically, that's somehow related to the non-perfect conservability of
the phase indicator, yes.
Yeah.
Of the color function.
Yeah, yeah.
You're right. It does not stay constant, even though with a mathematical and numerical trick, we are able to maintain it almost constant. Well, the typical characteristic of the method is such that you lose a little of this color function.
Yeah, so that's why you were talking before about the size of the droplets, which you can actually capture when your resolution increase, because basically you don't diffuse them somehow in the other phase.
Exactly.
Okay. Just a quick curiosity: when you say your resolution is very high because you use like 1,000 points or 500 points, they are spectral methods. We are talking about spectral methods.
We are talking about spectral methods, and the resolution is always of the order of less than the Kolmogorov scale, which is much finer than the usual resolution for the direct numerical simulation of single phase turbulence.
And just another very quick curiosity. So when you do like your simulation in your channel, so you have along the wall you use Chebyshev or Legendre polynomials?
We use in the cross distance, in the cross direction, which is perpendicular to the wall, we use the Chebyshev polynomials.
Okay. And the rest is Fourier.
And the rest is Fourier. Okay. But in the future, we will have to change it and switch probably to find a difference in the cross direction, because we have problems when we when we try to change the density of the mixture.
Yeah. Yeah, because you are enforcing basically through the base function, you're enforcing periodic boundary conditions, which somehow, when a droplet comes out.
Well, I'm not exactly sure how it is numerically, but definitely the problem becomes numerically a little unstable if you use density coefficients with very large difference.
Okay. Okay. So it's more related to. Okay. If I may ask, I have another question which is related to what you mentioned before regarding not the droplets but the pipe which you kind of studied using a channel flow.
Yes.
As far as I understood, so you are not enforcing a symmetry condition at the bottom, but you are enforcing a no-slip condition at the bottom of your channel, right?
Yes, of course. This is not exactly the topological modification I said before. That was just to explain that we just wanted to examine one side of the pipe, say. The point in which we were interested there, it was to examine if there was an effect of the surface tension on drag reduction. And we found that there is a huge effect of surface tension of drag reduction, even if there is no viscosity effect on drag reduction. So we thought that this was an interesting result, which was not actually examined before. Now we are running further simulation in this case, but you see the problem is that we could leave it open. Now the point, what we are doing is to put a low viscosity layer of water on top and the lower viscosity layer at the bottom, and in the middle of the channel we are putting the oil. But in this case, what happens is that the friction is so low that the velocity of the internal layer is extremely high. Now, just with these two layers, we are using the friction so much that the problem changes a little bit. So internally, we have a plug flow with no turbulence, and all the turbulence is confined into these very tiny layers. So we are having not numerical problem, but computational problems because we need to increase the resolution. So what I presented now is what we can currently track. We are doing a little more for the future.
Okay. So you basically replied to the follow-up of my question. Okay.
Yeah. Okay.
Is there someone else who wants to ask a question? I remind you that you can just unmute your mic or write in the chat, and then we'll report the question. Yeah. Please go ahead.
Sorry, I guess I will have a couple of questions. Hi, I'm Yves Dubief from University of Vermont. So really great talk. Unfortunately, I could catch only the second half. I was on another meeting before, but I'm looking forward to watching the first half later in the recording. So it's really interesting what you said about the stiffness of the equation and forcing you towards finite difference, because that's something that we have experienced in polymer flows for years. And in fact, we are starting to see ways to get around that. What's interesting too, what I find very interesting is that you're saying that you have to solve the Kolmogorov scale or smaller, right? Which again has been something that has plagued polymer drag reduction and then later on elasto-inertial turbulence research, where too many in the community have tried to run simulation with the typical resolution of Newtonian flows. And in fact, what we've discovered is that everything that is interesting happens close to the Kolmogorov scale. So my question to you is that, do you see any inverse energy transfer from the from the surfactant, from the like what's happening around the Kolmogorov scale towards the large scale turbulent structures?
Well, simple answer is I don't know. And this is actually a dream of measuring. I mean, we would like, I mean, what happens is actually in my simple mind, I have a simple explanation. And I can imagine that if I put energy into an elastic surface to deform the elastic surface, then at some point, this energy must come back to the flow inside or outside. So there must be an energy equation which is a little more complicated than the turbulent kinetic energy equation. Now we have published a recent paper. I think it appeared in March or April in Journal of Fluid Mechanics, in which we compute the energy balances between all these phases, and we find, of course, that the drag reduction. So this is just for the drag reduction problem, in which the balance of the energy is a little more important, because we need to come to an explanation of the drag reduction. And in that case, of course, we found that whenever we have drag reduction, there is an energy which goes into the capillary, we call it capillary energy, but it's the energy of the interface, and then it is transferred back in different ways to the different phases in different places. Now, of course, we could study a little more in detail this problem. We have not done that, but I mean, it's really an open question, and definitely there is a very interesting coupling between all this phenomena. The question you asked was related to the interface and also to the presence of surfactant. Now, we have not yet examined what is the energy, the amount of energy that goes into the surfactant, because anyways, if you move the surfactant and if the surfactant wants to come back, definitely you are shifting some energy here or there, and therefore you are changing the overall turbulence kinetic energy balance. We have not yet computed that.
So I have only one suggestion. It's really out of sheer curiosity. I would love to see a simulation like this. So in fact, recently we demonstrated that elasto-inertial turbulence exists in two dimensions, which from the perspective of numerical simulation is a tremendous relief, because again, like here we are running simulation at Reynolds 1000 or even 100, having a fully chaotic flow. But of course, we need very high resolution, right? So like in a 2 pi by 2 domain, the minimum we need to have is 500 square, or more. And I think you have exactly the same problem. So what will be, I think there is some evidence in the literature that surfactant, or at least cells, may create their own chaotic system, much like polymers create elastic turbulence and elasto-inertial turbulence. So if that's something that your group can look into, that there might be something really interesting there, because as you said, polymers are elastic. You have an elastic system, and as soon as you create some type of chaos, the question is, can you enter a self-sustaining chaotic regime?
Well, your direction of future research is extremely interesting, and the question is, of course, extremely interesting. And from what I think is that the system is purely elastic, so there is no dissipation through the interface and no dissipation in moving here and there the surfactant. There is no dissipation involved. The only dissipation mechanism is through of course, the usual turbulent dissipation mechanism. But what you suggest is we have somehow to, well, it's the range of parameters that scares me, because how much surfactants, where should I put it, how much interface? So, I mean, it requires a very good planning, but definitely it's worth investigating.
It's a very, very stiff problem.
Yeah.
I prefer to stick with my polymers. I will leave the surfactant to you. But thanks again for your great.
Thanks. Thank you.
So is there some more questions?
Well, I think that except for Vermont, it's aperitif time. So.
Okay, so.
That is correct.
Okay, fine. So I think if there are no more questions, we'll invite the audience to thank our speaker again. So thank you for the very very nice talk, and for replying to questions right after, for triggering the discussion. And so just a very quick announcement. So for this month, as you saw, we didn't publish a schedule yet, so we are trying to somehow arrange some talks. Whenever we will have some webinars, you will be notified by mail, webinar by webinar. So hope to see you all next time, and thanks again for the great talk.
Thank you, and thank you to the entire audience for the attention and the question, and for having remained here. Thanks a lot, Francesco. Have a nice evening. Bye. Good evening to everybody. Bye, Roberto. Bye.